Okay, in this video, we're going to do the notes for 7.3. So you can see that underlined HTTPS. That means if you click in there on the PDF version that's posted online, you can see a little video that will explain this by somebody else. But here I am to explain it to you as well, so you can use that as a reinforcement if you like. Okay, so let's go through these notes. Let me see where I am. So, as I said, we're going to hold off on the 7.1 and 2 quiz and continue these notes. Okay, so we're going to fill this in. So it says the altitude of a triangle. How do I define it? Well, it's the line. So let me turn my pen on. It's the line. Oh, maybe I'm not. What am I doing here? What is happening here? Hold on. Let me cancel that. And it should all work. So let me see if I can do that again. Yep, there we go. It's the line segment from a vertex to the opposite side of a triangle. Well, what does that look like? So let's say you have a triangle like this, and you want to drop an altitude. So come up here and go straight down. If you go straight down, which is the shortest distance between 2 points, it's going to make a right angle. Okay, so it makes, this says makes, a right, RT is my abbreviation for right, angle. Okay, a geometric mean, I want you to know, is a type of average, and we're going to do a lot of things with geometric mean. This you should know already. Similar polygons or shapes with congruent or just equal angles and proportional sides. Okay, when you reduce the proportional side, don't you get the scale ratio? Just to refresh on that. Okay, what's this altitude theorem? Well, it says that if the altitude, so altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar. So what does that mean? Their angles will be equal and their sides will be in proportion to the original triangle and to each other. So look, this is your original triangle right here. It's triangle, they're calling it C, they're calling it A, B, C. If you drop an altitude and it's drawn to the hypotenuse of the original triangle, so that means you got to do it from here, right? What happens? Well, this triangle that's formed and this triangle that's formed are similar, and guess what? The entire big triangle is also similar to each of the little ones that were made. And they changed the orientation here so you can kind of see it a little differently. So we're going to play around with this. This is going to be a very, very important concept for us. Okay, let me go back to my notes. So, do I want to do anything here? Probably. So let me tell you that you have a textbook. And if you want to look through this, it's on page 443 in the textbook. So what do I know? Let's just kind of play around a little bit. What if I put some angle measurements on here? You can probably then see this a little bit better. So let's just say, for example, if this was 35, then the other angle inside that same triangle would be complementary. That would be 55. What else do we know? Well, we know that, let's see, we know that we're going to form two similar right triangles. The bigger of those two angles will be 55. That's going to go here, and 35 is going to go here. Okay, got that? So what I'm seeing is this. if I drew these triangles out, and I have to a certain extent right here, put 35 here, put 55 here, 35 here, 55 here, wouldn't you say that triangle ACD by the angle-angle postulate has to be similar to triangle CBD? Okay, then let's look at the big triangle. That's the black triangle. I want to know what angle matches the 35. Well, let's see. It looks like angle A does. What angle in the big triangle matches the, let's see, the C would be the 55. Well, it looks like that's angle B, and one angle's left, angle C. So this is the big triangle. Angle ACD is the red triangle. So we'll say big, let's just call it the black triangle since it's written in black. So this is the black triangle, this is the red triangle, and this is the blue triangle. And look, they are all similar to each other. Okay, so you may have to go back and think about that a little bit. Now, how did I know? Do you understand how I got these angles up here? Once you got the 55, this was a previous right angle. So that means that this has to be 35, which makes that 55. So you can just play with it and put angles in as long as they make sense to kind of see how to write these similarity statements so that you are matching up your angles. Okay, so look what's going to happen. Angle A in the big black triangle is 35 degrees. Angle A in the red triangle is also 35 degrees. And angle C in the blue triangle is 35 degrees. That's great. Angle B in the black triangle is 55. Angle C in the red triangle is 55. And angle B in the blue triangle is 55. And then angle C is 90. Angle D is 90, and angle D again is 90. So by angle similarity, we know that those three triangles must be similar. Okay? Similarity. Okay, excellent. So that's what I'm seeing. Okay, let's continue with the notes. Okay, remember I said that the geometric mean is a kind of an average. So let's see what I mean by that by taking some more notes. So here's the first thing I want to think about. So I'm going to make this my point 1. Okay, the geometric mean as it pertains to altitude. Okay, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude is the geometric mean, kind of an average, of the length of the two segments. Okay, let's draw this out. What if I had a right triangle like this? Okay, and let's make this B, A, C. And that what they're saying in a right triangle, the altitude from the right angle to the hypotenuse. So if it's an altitude, you have to come out of the right triangle and drop it so that it forms a right angle. Okay? So that altitude, so what is that altitude? It's the red line. It is the geometric mean of the lengths of the two segments that are formed. Okay, so that means that when these two segments are formed, there's a certain relationship. So look what I mean by that. And I'm going to tell you that we're going to do fraction equal fraction to do that. So I will tell you that the geometric mean, and we'll make this CD, always goes low, high. So this is low, this is high. Okay, so that's CD, and this is also CD. The geometric mean always repeats. Okay, so in this box is where the geometric means go. Then the missing pieces are one little segment and the other little segment. And if you had numbers, you would see that that would work. So let me put some numbers in here. What if I make this a 10 and this a 2 and this a 50? Look what's going to happen if we try this formula. So remember, the geometric mean goes low, high, okay? And the geometric mean is the altitude. So put that twice. Then put the other two numbers. Do your cross products. 10 times 10 is 100, and that equals 100. Okay, we're going to do more of these things. So the first geometric mean has to do with the altitude. The next one has to do with the leg. So the geometric mean leg theorem is my second one. And that says in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two equal segments. Yep, we know that. Then we go on to say the length of each leg of the original right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that's closest to the leg. Okay, that seems terribly confusing. So let's try this again. So I'm going to draw the exact same triangle. And the reason why I'm going to do that is to cut and paste. So I'm going to say, let's copy that. Let's paste it here. Okay, so I'm not so much interested in the numbers this time. So that's going, that's going. I am interested in the letters. So, whoops, I didn't want to do that. So let me go back one. And let me just do that. Okay, so if we're talking about the legs, let's focus on leg BC. So we said that it is acting as a geometric mean, which is kind of an average. So remember, we always put the geometric means low, high. So that means that if we're doing leg BC, it's going to go here and here. And it's the geometric average, or the geometric mean, between the piece of the opposite side closest to it. So that's going to be, now I'm doing this. Okay, so leg BC, I put it there and there, and then we have BA. Oh, yeah. It's a geometric mean between the entire opposite hypotenuse and the piece closest to it. That's for leg BC. What happens with leg CA? Well, if I'm going to do leg CA, guess what I'm going to do? Fraction equal to fraction. Where does leg CA go? Low, high, right? Because it's acting as a geometric mean. That's where the boxes go. And it's a geometric mean between the piece of that opposite side closest to it, which we can say is DA, and the entire opposite side, which is BA. So that's how that works. So this makes no sense until you start practicing it. So I have it there. You may want to listen to it again. Key things are where I'm putting the geometric means. Let's practice. this says find y. Okay, I'm going to find y, and when I do that, I have to recognize that this is similar to finding a leg, right? So that was example 2. So I know that the leg, which is y, is the geometric mean. That means it's going to go here, and it's going to repeat y and y between the piece of that original hypotenuse closest to the y and the entire thing. So 3 times 9, cross products, 27 equals y squared. Y equals radical 27, and you know how to break this up into 9 times 3, 3 times 3, bring down your 3, put everything under a radical, circle your pair. If it's circled and comes out, it's no longer in. So I'm finding that y, which is the leg, is equal to 3 radical 3. Okay? Let's do another one. Look at this one now. Same idea. I'm trying to find a leg, so I'm still working with that second theorem. Find the value of k. Well, k is the leg, and the leg is defined as a geometric mean. Here are the geometric mean boxes, low and high. Put the k both places, and that's the geometric mean between the piece of that hypotenuse closest to that leg and the entire hypotenuse. So therefore, k squared is going to be 2 times 10, which is 20. I don't want k squared, I want k, which is radical 20. Over here, break that up into 4 times 5. And then 4 is 2 times 2. Bring down the 5. Put everything back under the radical. Circle your pairs. They come out as a single. If they're out, they're not in. So I'm going to get k equal to 2 radical 5, and we're done. Okay, so now it says use the diagram at the right, and it's actually below. Which proportion is true? So let's see. First off, I'm going to tell you that you've got 3 geometric means, here, here, and here. And when we set this up, what we always do is put the geometric means in the low-high position. Okay, so I need either AD in low and high. Okay, so this is possibility. Okay, so maybe. AB is not a geometric mean. It can't be in the low-high. And what about DB? Oh, DB could be, because DB is a geometric mean. It's the altitude. So remember, this is the leg, and this is the altitude. Okay, is it true if using AD, that's a leg, so the leg is a geometric mean between the piece closest to it, which is AB, and all of the hypotenuse, which is AC. So this does not work. It looks like it's this. Let's just check it. So I have my DB, which is the altitude, placed correctly in the geometric mean spot, and then that's the geometric mean between each of these pieces. So AB and BC, bingo. This is the correct answer. Okay, so that's the end of the notes. You may need to look it over again very carefully and listen to what I'm saying. Let me tell you what is going on here. So we're looking at this and we're saying, okay, can I do this homework? Go back and look at my notes and see if you can figure out how to write similarity statements connecting all 3 triangles. My suggestion would be this. Pick a random number that's going to be less than 90. If this is 30, this is 60. If that's 60, that's 30, and if that's 30, that's 60. Use that information to then go ahead and find your correct similarity statement. Okay? So that's my thought on that one. you have the big triangle and the medium-sized triangle and the little triangle. So think about that. Let's look at this next one. Why don't we do the same general idea so that you can pair things up, because you're going to use the similarity statement based on angle-angle similarity. So what if we said that this was, I don't know, 70? Make this 20. That has to be 70. That has to be 20. Use those angles to help yourself write the similarity statements. And you've got to have, remember, you've got to have the big triangle is similar to what? The medium triangle, which is similar to the small triangle. And I went into great detail how to set that up, so go back and look at the notes. What else do we know? Here's more homework. Okay, so you have 3 geometric means. This is the altitude. That's going to go with theorem 1. This is the altitude, also theorem 1. This is a leg. That's going to be theorem 2. Look back at the notes. This is a leg. That's going to be theorem 2. Here is what's missing is this, but this is an altitude, so that makes it theorem 1. What's missing is the whole piece, but they give you the little piece, therefore this is going to be theorem 2 based on a leg. What's happening here is you're focusing on the leg, so this is going to be theorem 2. Think about that. And what's happening here, you're focusing on the altitude, so that's theorem 1. So that should get you started. So look back and see how I set things up. Remember that you're going to always put the geometric means, whether they be the legs or the altitudes, in the low-high. They will repeat. These will always be the same values. They'll, and then the other two, it depends on whether you're doing the altitude or the legs, but you've got to go back and really think about this. It's going to take a little while to click, so you've got to be patient, and we'll go over it when I see you again. I hope this helped.